The computer era has witnessed an explosive growth. The growth of hardware power and variety has been matched by software systems of increasing power and variety. Special supervisory software systems, known as operating systems, have evolved to help managers, analysts, programmers, and operators control and allocate these software and hardware resources. In fact, understanding operating systems has become fundamental to understanding how people, hardware, and software interact in a modern computer installation. In this lesson, you'll learn why operating systems are needed, what facilities a typical operating system provides, and how operating systems work. This chart helps us to see why operating systems are needed. It shows the times required for a stream of computer jobs. The time shown between jobs is needed for setup operations. Setup time includes initiation operations, such as mounting new tapes and changing printer forms before starting the next job, and termination operations, such as dismounting tapes at the end of a job. Here we see what happens as hardware power increases. Jobs take less time, but setup time remains the same. Since a computer is idle during setup time, potential processing power is unused while initiation and termination operations are performed. Here we see the effect of using an operating system to reduce setup time by assisting operators wherever possible. For example, by printing messages telling when and where to mount tapes and disks. This also assists installation management by keeping accurate records of system utilization and by increasing the number of jobs which can be put through the system over a given period of time. This improved system performance is called increased throughput and is one of the major objectives of any operating system. An operating system can assist analysts by providing special languages to control several programs working together to accomplish jobs. Such control languages allow the analyst to specify job steps, programs, procedures, and data to be used for each job. Here are some simplified control language statements for a typical job. A job statement shows the beginning of each job. A job may have several interdependent steps, such as compile, load, and go. An execute statement shows the beginning of each step and names the program to be used by the step. A data definition statement describes data sets used in the step, one for each data set needed. A data set, such as source coding for a compilation, may be put in the job stream following a data definition card like this one. Some type of delimiter card may be needed to separate stream data cards from control language cards. Some operating systems allow whole control language sequences to be placed in a procedure library given a name. Such cataloged procedures can then be referenced by a single control card. Such facilities can greatly assist programmers by simplifying job requests and reducing mistakes. Many operating systems also provide system generation and configuration maintenance facilities which can relieve the programmer of concern about the current status of the computing system. Operating systems can also assist operators, managers, analysts, and programmers by providing flexible scheduling procedures. For example, if jobs are submitted in a batch and executed sequentially, this job, for example, must wait until all these jobs have been completed. However, by assigning priorities to jobs, this sequence can be flexibly changed, shortening the time between submitting a job and receiving results. This measure of system performance is called turnaround time. Reducing turnaround time is another major objective of many operating systems. An operating system can accomplish its objectives by providing resource allocation facilities. These facilities are often classified by their functions: job management, data management, and task management. Job management facilities control the flow of one or more jobs from an input stream. A routine is usually provided which accepts operator commands or inquiries and sends him messages about the status of a job. This kind of routine is often called a master scheduler. Typically, a facility is also provided which reads the input stream, recognizes job control statements, interprets them, and transcribes the input stream to direct access storage as an input queue or waiting line of jobs to be processed. Another facility, usually provided by job management, is an initiator-terminator, which reads job control data from the input queue and allocates resources such as input-output devices. When no longer needed, these resources are returned to the system by the terminator. Effective data management provides another example of how an operating system can improve resource allocation. Data management typically includes facilities often called access methods for retrieving or storing logical or physical blocks of data from several possible data organizations, such as sequential, indexed, direct, or partitioned. Here's a program which requires input, processing, and output operations. In some early computer systems, the central processing unit had to remain idle during input and output. These operations can occur at the same time on computers equipped with data channels and provided with data management facilities for effective channel scheduling. Here, processing has finished before the input-output operations are complete. The central processing unit is again idle. This situation can be improved by effective task management, which allows tasks that require processing to share the central processing unit during input or output operations. When input-output operations are complete, control of the central processing unit can be returned to the original task by interrupting the task in control. With channels now available, data management facilities can initiate more input-output operations for yet another task if necessary. The simplest kind of task management is illustrated by a sequential scheduling system. Here, each job step is executed as a single task. The initiator-terminator and the reader-interpreter functions are executed as single tasks between job steps. Multitask management can be accomplished by a system which allows multi-programming with a fixed number of tasks. Each task is assigned a fixed partition in storage. In this example, we have a data communications task which receives control if it's needed. If not, task 2 receives control if it can proceed. Otherwise, control passes to task 3, shown here as a job step in a sequential scheduling system which is processing a job stream. Task 2 might be a utility program that prints output data and transcribes input data for later processing by task 3. A more sophisticated form of multitask management is illustrated by a system which allows multi-programming with a variable number of tasks. Each task is dynamically assigned a storage region which is variable in size. In this example, tasks 1, 2, and 3 are running concurrently. When task 1 finishes, task 4 and task 5 are dynamically assigned. Notice that the control program is now executing 4 tasks in 4 regions. Let's review. In this lesson, you've learned these fundamental operating system concepts. Setup time. Why operating systems evolved. Throughput. Job control language. Cataloged procedures. Priority scheduling. Turnaround. Job management. Data management. Task management. Sequential scheduling. Multi-programming with fixed tasks. Multi-programming with variable tasks. These concepts are basic and necessary to understanding any operating system.